Good day, viewers. My name is Usman Abdullahi Usman, a postgraduate research fellow in the Department of Geology, Faculty of Science, University of Malaya here in Kuala Lumpur, Malaysia. I'm here to present a brief research findings titled Characterization of Iron Ore in Upper Layer Alluvium coupled with mineral phase equilibria and solubility in shallow groundwater of Lower Kelantan Basin, northeastern coast of Malaysia Peninsula. The significance of this research study is basically on two key points. One, this characterization methodology has not previously been applied to understand this iron hosting sediment in the state of Kelantan. Secondly, this work shows that the sources of the transition metals contamination in groundwater can be from local, shallow sources, and that collection of hard data for acquired media mineral composition is essential for understanding of the source and effect of soluble metals. Our future plan work is to come up with cost-effective and efficient remediation method that can be used to minimize the high concentrated metal in the groundwater of the research area. This figure 1A and B is optical light images for iron ore and other minerals. Iron-bearing minerals observed under optical light images in these studies are chlorite, goethite, and hematite. Thin layer of chloride coatings were clearly seen on the grain surfaces. And the thin layer of chloride in these samples are distinguished from kaolinite, which they are colorless and white to pale yellow birefringence, while elite are bright birefringence. Most of the chloride in these samples are light to dark green color. Both hematite and goethite are slightly elongated spindle habit. Generally, goethite are formed as a result of early precipitated colloidal iron oxide, and hematite were formed as a result of diagenetic recrystallization of goethite. Figure 1C is FISM images showing mineral composition and morphological features of chloride, kaolinite, and subordinate elite. As you can see, the figure shows clear mineral dissolution framework. Generally, clays are very sensitive to fluid chemistry, and clays are having high cation exchange capacity. Most likely, the iron ores are soaked onto these clays, probably on the surface of chloride, because kaolinite has low cation exchange capacity. Table 1, it shows elemental composition of the mineral in the alluvial soil sample that obtained from energy dispersed X-ray analysis. As you can see, the result, it shows high concentration of potassium with significant amount of iron. And this is the main constituent of iron-bearing minerals in the samples. Figure 2 is FTIR spectrum of one of the sample, and all other samples, they have the same patterns. Goethite bands arises because of other polymorphs or iron oxyhydroxide from the iron oxide and hydroxide vibration. As you can see here in this sample, the two less intense band within the frequency range of 3,600 to 3,700 are attributed to the bending vibrations of surface hydroxyl group of goethite. Hematite characteristics were also detected at quartz-free zone, specifically within the low frequency range between 400 to 500, as indicated by two intense bending vibration. Other goethite, kaolinite, and absorbed water were also detected in all the samples. Figure 3A is XRD bulk analysis. As you can see, the result shows range of oxides associated with clay mineral suits. The high concentration of gibbsite in this sample, it is an indication of the lateritic weathering profile, the existence of lateritic weathering profile within the basin as a result of ion leaching. Figure 3b it shows a clay fraction XRD analysis, and the result shows non-swelling clays in all the samples with clear diagnostic features of chloride. Although distinguishing kaolinite from chloride is subjective, but indicate that any chloride present are likely ion-bearing chloride due to the collapse of 002 and 004 peaks on heating to 550 degrees Celsius. All other chlorides are stable at this specific temperature, kaolinite breakdown. Therefore, the presence of ion-bearing chloride in this sample adds us uncertainty in this interpretation. Figure 4a is a thermal analysis for the alluvial soil sample, showing specific endothermic geotite peaks within the temperature range 400 to 500 degrees Celsius. The reaction that took place within this temperature range is as a result of the composition of the geotite matrix. Figure 4b, it shows the Raman spectra of the octahedrokaolinite and the characteristics of hematite cutting quartz. The Raman spectra of the octahedrokaolinite spectrum is divided into 3 regions. As you can see, the peaks that occur within the range, within the frequency range below 600 are from set of complex cation translation motions that link to interlayer site and octahedral sites relative to silicate groups in oxygen hydroxides and interhedral layers. The peaks that occur within the range between 600 to 800 are from vibrational bonds that are attributed to silica bridging bonding vibration that link to tetrahedral silicate layers. Then there are some less peaks that occur within the frequency range between 800 to 1150 are attributed to the bending vibration of silica non-bridging oxygen that link to tetrahedral silicate group layers. And the spectrum beside it here is a typical example of hematite coating quartz. As you can see, at 1383 is attributed to hematite, and this intense peak at 488 is attributed to quartz. Figure 5.1 and 2, it shows, figure 5.1, it shows pH versus saturation indices for ion-bearing mineral phases. Saturation indices for mineral phases were developed on the basis in which pyrite and the hematite were supersaturated in the groundwater samples. The siderite is at or close to equilibrium. As you can see, ferrihydrate, most likely they are metastable equilibrium. The most stable iron oxyhydroxides in these samples are all saturated, and this could crystal the iron in the solution. All other minerals like magnetite, melanthite are undersaturated. Figure 5.2, it shows iron oxide, hydroxide, and sulfide equilibrium phase diagram. Speciation simulation of AOGS were performed in equilibrium and redox equilibrium and disequilibrium method to measure redox couples centered on the calculation of ferric ferrous and sulfate. The mineral phase stability relationship here indicated that oxidizing condition most likely dominating the groundwater within the basin. And the ferric ferrous and sulfate groundwater samples indicated that, as you can see here, hematite as stable phase. The groundwater sample also indicated siderite at this equilibrium. And other sample shows the stability relationship, borderline stability relationship between the iron carbonate and the siderite. So in conclusion, the integrated method used in this research to study iron ore and clay minerals concentration of lower Kalimantan Basin alluvium provides significant and detailed information about their mineralogical, morphological, and chemical composition. The mineralogical composition provides insight into the environmental conditions that predominated during the post-depositional diagenesis that produced the iron ores. This study indicates that mineral phases, especially iron oxyhydroxide, usually believed in low temperature aqueous environment are stable, can be a considerable source of iron ores under specific physicochemical condition. The relationship between XRD result and the groundwater modeling is indecisive, as hematite and siderite are a low match, and in some samples are no evidence of their presence. Finally, the relationship between the thin section petrography result and the speciation simulation of aqueous confirm the presence of iron oxyhydroxide. Thank you very much for listening. Thank you.